not. All right, so let's go ahead and get started with the proof. Okay, the proof, yes. We have to rigorously prove everything in this class. Oh, by the way, yesterday I was in a meeting that discussed, basically whether this class should be listed or be accepted as one of the GE classes for reasoning and logic and stuff like that, and it was approved. So starting 2011, after the summer, this class will be officially accepted as a GE class to fill the reasoning or logic part of the GE requirement.
Is it retroactive to this for this?
I do not know. You have to check with your counselor to see whether you can use a GE classification that is going to be done in the future, like next year in the summer. If you have not graduated yet, I think you may be able to use it.
You can.
You can?
You can use whatever current one it is. It's just typically you want to use your own catalog rights from when you started.
Okay.
That's when you plan it.
Right. But if it is advantageous to use a newer one, you can.
Yeah, then
Okay.
you can.
Okay, so I guess it is an option if you have not graduated yet by next summer. So that's good because once you have taken this class, it will fill one of the GE requirements. When I was in college, I dreaded GE classes. I took all the major classes first within the first 2 years, and then I took all of the major classes in computer science. Then I had to drag my feet to take the GE classes. Like, oh no, I have to take GE now.
Who doesn't want to take symbolic logic?
I took all the computer science classes, all the physics classes, all the math classes that I need for my degree, and then there was nothing left after the second year. Then I have to take all the GE classes like psychology, philosophy, and that sort of thing.
So what's the deal now that we got to take PE classes though? I got to go and take golf or bowling or yoga or billiards or something else.
I think part of that has to do with the the PE department has to somehow prove that it is required for college. Because I think there are a lot of people saying that if funding is shrinking and the college is not getting enough money, we should cut PE classes first. Right. So that's why they have to kind of put PE classes into the requirement so that everybody has to take some of their classes.
It's not a transfer requirement for some schools.
It is not for most. Yep, it is not for most.
You won't get your AS degree or AA unless you got it. So.
Yeah, but many people in this class do not really care because all they have to do is to go to assist.org and find out what classes actually transfer to which school in which program and only take those specific classes. Some people do not even care whether they get an AS degree in computer science because that degree has no meaning to these people. Yep. And I can fully understand why, too. Okay, so getting back to this claim here, remember we talked about proof by contradiction. So we'll go ahead and try to prove this by contradiction. But before we do that, I just want to make it clear that you will not be asked to prove anything like this. You will not be asked about proof by contradiction. This is just a little bit of exposure so that you guys know what it is and why it is important to have, mathematical proofs. When you work on an algorithm, you have a good idea of how to optimize it, but how do you know for sure that the optimization is correct? It does not break the code itself. Okay. So here is the proof by contradiction. Let's say Tech was wrong. Okay. Now, it's easy to say that Tech was wrong, but what exactly does it mean when Tech was wrong? Okay. This means that someone can find a greater than 1, b greater than 1, n equals to a times b, all integers, and yet a times a is less than or equal to n, or b times b is less than or equal to n is false. Is that okay so far? Because when you talk about proof by contradiction, the first thing you need to understand is what does it mean when I say the theorem was wrong, was false. In this case, the theorem states that if you find A is greater than 1, B is greater than 1, n is defined to be the product of those two numbers, this has to be true. So to say that the theorem was wrong, you still have to find me these numbers, okay, and define n appropriately. But yet, this statement is no longer true. Is that okay so far? Yes? Okay. Now, when this condition is false, what does it actually mean? This is the same as to say not A times A is less than or equal to n, or B times B is less than or equal to n is true for some A greater than 1, B greater than 1, and n equals A times B. Right? Someone, if the theorem was wrong, then someone can find a counterexample where the requirements of A and B are satisfied, and yet the statement is false. Are we doing okay so far? So now I have to say not A times A is less than or equal to n, or B times B is less than or equal to n. It's really saying the same thing as not A times A is less than or equal to n, and not B times B is less than or equal to n. Let me use extra parentheses just so that we can show that the negation happens first and then the conjunction is on top of the negations. Is that clear? It doesn't seem very clear to me. The negation of the disjunction is actually the same thing as the negation applied to each component, the negation to each component, and we have a conjunction of them all. It doesn't seem to immediately follow that this has to be equivalent. So first of all, I have to prove that that is actually true. Okay? In other words, what I'm claiming is if you have the negation of some condition x or with some condition y, it really is the same as saying not x and not y. Does that make sense? Seems to?
You're saying one or the other has to be true, so to make you wrong means that both have to be false, right?
This statement can only be true when x is false and y is false.
Right, I mean, in the original statement, you said one or the other has to be true.
Mm-hmm.
So the opposite
But
would
I'm
be
also
that both
saying-
have to be false, right?
But I'm also taking the negation of that.
Yeah.
Yeah. But can we establish this first? Because that's important. Once we can establish this, then we can apply it over here. Can we prove it? Well, in Boolean algebra, it is easy to prove something, right? Because what we can do is now we can use a table. We can say, let's enumerate all possible combinations of x and y. Then we'll go ahead and calculate or derive what is the value of this expression. And we'll also go ahead and derive this equation here, or this expression. Okay? X is a Boolean. How do I know X is Boolean? Just by the context. How do I know X has to be a Boolean type of value? Yep. Because it's on one side of the OR. Okay? Because you can only use Boolean or true-false value on both sides of OR and AND. So we know that X is either a true or a false, and Y is also either true or false. Given that, then we know that X can be true, X can be false. When X is true, Y can be true, Y can be false. When X is false, Y can be true, Y can be false. Are we okay so far? This is basically enumerating all possible combinations of X and Y. Yes? Okay. So with all the possible combinations enumerated, can we work on the actual value of not X or Y? What do you think the result of that should be? False. Very good. It would be false here. And how about the second one? False. Third one? False. Last one? True. Very good. Now we work on the other one. What do you think would be this one? It'll be false. Very good. And it's this one would also be false. How about the next one? False. How about the last one? True, because x is false, not x is true. Y is false, not y is true. True and true is true, and that's the only case that we can get true. So you look at this table, and what do you notice? You notice that this column is exactly the same as the other column. So what it is telling you is this expression is exactly the same as this expression here for all possible values, for all possible combinations of values of x and y. So that's it. That means that this expression is equivalent to that expression. The next question is, why do we bother with this? I mean, this is so much easier and this is longer. So why do we bother to do the transformation?
You can rewrite the inequalities.
You can rewrite the inequalities. It's actually easier to evaluate the inequalities in this form. How many people here, want to become or want to get into a computer engineering program or an electrical engineering program? You guys will see this day in and day out because this is also called De Morgan's law. De Morgan's law basically can transform ands into ors and also vice versa. It can also transform ors back into ands with negation. You will see that in electrical engineering as well as computer engineering, they don't have AND gates natively. They don't have OR gates natively. They only have NAND gates, N-A-N-D, and NOR gates, N-O-R gates. Those are native to devices, okay? Which means everything that you express using these logic eventually have to be converted into NAND and NOR gates. And De Morgan's law is very, very helpful when you need to do that conversion. Okay? But that is a topic that should be left to a 4-year university, but you will see De Morgan's law over again and again and again. It's a very useful type of transformation. Okay, so once we have this, we can establish that this part here has to be right, has to be true. Okay? And this is all based on the assumption that I was wrong to begin with. Don't forget that. Is there an easy way to rewrite this part here? It is not the case that a times a is less than or equal to n. Greater than n? Very good. So we can just rewrite this one as a times a is greater than n. And the other side, same thing. B times b is greater than n. Can I go from here and say that this implies that a times b is greater than n times n? Is that implication okay?
Yeah.
We know that a is positive. We know b is positive. We know n is positive. So is that okay?
Yeah.
That step is fine? Okay. So, but doesn't that also imply that we can just rearrange a and b a little bit so that we can have a times b times a times b, just like that, because of the commutative law of multiplication? Commutative means you can exchange the order between two operands of the same operator. Now, if I group things into a times b and a times b, that should be fine too, because the order of the evaluation of the operator is not important when you have a bunch of multiplications. By definition, what is a times b? N. A times b is n. So now we have n times n is greater than n times n. It is a contradiction. It can never happen. So this is all a result of negating my theorem to begin with, which means the theorem itself has to be true. In other words,